So our change of base formula allows us to calculate these different logs, like this one, log base 3 of 14. Now, we can check that, right? So after you type it into your calculator and you get that it's 2.402 something, that allows us to check it. And let's see if we can't figure out a way to check it. 2.402 dot 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 dot, meaning it's going on forever. But let me write it like this. Log base, yeah, it's supposed to be a 3. Log base 3 of 14 equals 2.402 dot dot dot. The way to check this is if I rewrote it using exponents. How would I rewrite this using exponents? What would it look like? What to what power? Angel? Beautiful. Thank you so much. 3 to the 2.402 dot dot dot. 2.402 dot dot dot. That equals 14, or should equal 14. Now, your graphing calculator gives you a cool way to do this. So what you can do is raise 3 to this power. Now this number, all its digits, is stored in answer. So you hit the second key, then the opposite key on the bottom, and what should I get? I should get exactly 14. Now, if you don't feel like being that fancy, or if you're doing it in Desmos, and you're like, well, Desmos doesn't quite do that, you can do 3 raised to the, I don't know, I'll just do 2.402. Now it should get me close to 14, but I'll probably be a little bit less, 13.997 or something like that. So there. So it's close. It's convincing enough, is what it is. Awesome, awesome, awesome. Now, we're gonna work on our properties of logarithms. And that's going to start with these right here. So if you're watching this later, pause these, write these down. And in particular, some of the ones we're going to use are really, really handy. Like this one, log base b of b. What power of b gives me b? 1. Or another one that kind of follows from this is log base b of b to the x. Now, I'm going to write the answer over here, but I'm going to prove it as we go down the page here a little bit. So, how would I prove that? Well, one of the properties of logs that you can see here is this one right here. It's the power rule. And the power rule says this exponent can come out in front and multiply everything. So I'm going to bring that x out in front and write this as x times log base b of b. And there's good news. We just figured out what this was, right? What is log base b of b?
1.
It's 1. So, wow. So what happens when you have log base b of b to the x? It's just x. And that really shouldn't be a surprise, because when we created these properties, when we created the logarithm, it was because it was the inverse function of the exponential. So doing the log base b of b to the x, that's like taking the cube root of x cubed. They're opposite operations of each other. One does something, the other one undoes it. So, nice. Now, we're going to use these properties in 2 different directions. One of them is going to be starting on the right-hand side of this to squeeze things together, write them with one logarithmic term. If you look on the left-hand side of all these properties, there's just one logarithmic term. But over here, there's 2. Over here, there's 2. So I want to rewrite things with one logarithmic term. I'm going to use these properties. In my mind, it's kind of the backwards direction. Usually I think of it as expanding these things, but now we're going to take them backwards. So let's do that with this example. Example B. 2 times the log of x plus log of y minus the log of z. Oops. Didn't realize I was off screen. Sorry about that. So 2 times the log of x plus the log of y minus the log of z. Now, in order to use our formulas, what I need to do is I need to have the coefficient of 1 on all these logarithmic terms. Now, there's a coefficient of 1 there, but there's not one here and there's not one here. So to get a coefficient of 1, I'm going to use my power rule in the opposite direction. So I'm going to take this and bring it up here. And I'm also going to take this exponent and bring it up here. Now, especially with that latter one, you might be, well, what exponent do you mean? Well, right here, that's log of x squared. This stays the same, that's the log of y. But here, I'm going to bring up the negative 1. So that's log of z to the negative first power. This is probably different than a lot of what your other instructors might have done for a problem like this. But there's a nice savings in effort when we do this. And part of that savings comes from right here. When you have the sum of these logarithmic terms, the sum of the logs becomes the log of a product. So I can do this right here. I can rewrite this as log of x squared y z to the negative first power. Now, if WebAssign says write this using one logarithmic term, you're done. Let me give you a heads up. Your instructor is going to want one more thing. I'm going to want you to write it without any negative exponents. So the last step that you need to get full credit would be this: log of x squared y over z. Beautiful. That's all I'm looking for there. All right, how are we looking on that one? Doing all right? Let's do a couple more here. I'm going to evaluate things. I'm going to evaluate a couple examples. And this first one, example C, I've got a couple parts to it that I'm going to do in different ways. So the first one is negative 1/2 log base 5 of 25. Now there's several ways you could do this. And the first way is going to look like this. We should be able to evaluate log base 5 of 25 just in our heads. The question this is asking is, what power of 5 gives me 25? 5 to what power?
5 to the second.
Squared, perfect. And negative 1/2 times 2 is negative 1. Done. End of story. Nice. So that's method 1, or approach number 1. Let's take a look at a different approach. I'm going to bring that negative 1/2 up into the exponent. Actually, you know what? I'll just bring out the, I'll keep the negative here. I'm going to bring the 1/2 into the exponent. What's 25 to the 1/2? What's something to the 1/2 power?
Square root.
Square root of 25 is 5. Nice. And now I'm going back to one of our properties again. What power of 5 gives me 5? 1. The negative's still out in front, so I get negative 1 again. Now, you can also calculate log base 5 of 25 directly on your calculator. Your newer up-to-date graphic calculators have this. Let me remind you where that's at. If you hit the math key, then hit alpha and then the A key. that will take you down to log of any base. Now I'll cursor up to get there, but you can get there directly by alpha and a. So here you go, log base 5 of 25 gives me 2. Beautiful. This is not on the 83. The 83 is kind of old school. The 83, let me sit down here. Yeah, the 83 was released in 1996. So, but you know what? The 83 is still a great calculator, still does a lot of cool things. It's just not up to date to keep up with some of the cooler features on these things. Let's keep going. Next one I want to work on is log base 2 of the square root of 2. So this is still part of example C. Log base 2 of the square root of 2. Probably a couple ways you could do this one. Probably a couple ways you can do almost all problems. But let me take this approach. Let's rewrite the square root of 2 as 2 to some power. How could I do that? Oh, well done. Who got that? Is it Julian? Well done. This is really 2 to the 1/2 power. Now there's 2 ways you can do this. It depends on which of these formulas you want to use. But for my money, I'd use this one. When you have log base b of b to some power, these things cancel. What's my answer here?
1/2.
1/2. It's just 1/2. That's it, you're done. You could alternately take the 1/2 out in front and then use this power. You'll have log base 2 of 2, which is 1 times the 1/2 out in front, still gives you 1/2. So whichever of these 2 properties you want to use, the one circled in orange or the one circled in blue, both of them work. All right, nice. Let me do one last one that's kind of part of example C, or at least what I'm calling example C, and it's kind of a long one. So, and there's something in particular I like about this problem. Before I get there, Sydney's got a question.
I got 1/2 without doing any of the middle work, just because it was already kind of set up to do like 2 of x equals root 2. Do we have to show that middle step?
I'd probably be most comfortable if I saw something.
Okay.
I mean, the challenge that I face is that sometimes you can do the wrong thing and get the right answer. For instance, 64 divided by 16. Oh, hey, let me cancel the 6's. That gives me 4/1. Hey, I got the right answer. Well, yeah, you got the right answer, but you know.
I've never seen that in my life. It's a different one.
So yeah, sometimes depending on the problem, I get a little nervous when you just jump to the right
Has
answer.
anyone ever done that?
Probably just me, but there is something else that that I will show you about a different interpretation of a problem, which you might be interested in.
I'm very interested.
Okay, let me get down to the last part of example C here. And I like this one because you simply can't calculate this one on a calculator. It just won't work. It'll blow up your calculator. Calculator doesn't have enough digits. And it's the ln of e to the e to the 100. Yeah, yeah. Even your graphing calculator, which can hold a number as big as a Google, will choke on this, because that's bigger than a Google by far. Now, how do you work on this one? Well, the key in this one is to realize a couple things. And one of the things I guess I'll remind you about first is that ln is really a different notation than I sometimes write. ln is log of what base? It's log base e. Now, you will probably never encounter a textbook or any place else outside of this classroom where somebody writes it as log base e. But that's what it is, and it's helpful to remember that because we get some nice cancellation here. That's going back to our nice little rule over here. Log base b of b to some power, that's just going to be the power. The question is, what's the power in this problem? Where is my exponent? It's the whole thing in blue there. It's the e to the 100th. So that's what's going to come out in front. And let's be careful where it comes out in front. It's going to come out in front of this logarithmic term. So log base e of e to the 100. Man, it's nice that they choose to blow the leaves off of whatever right now. Log base e of e to the 100, or of e to the 100 times log base e. And what's going to be left in here after I take all that stuff out? Just an e. I got an e here and an e here. So now let's work in the parentheses. What's log base e of e? That's 1. So those formulas I told you to write down and put a special place in your note, here we're using it again. Log base e of e is 1. So that's kind of cool. That turns this into log base e of e to the 100. Let's see, I'll just keep it in this e to the 100. Technically there's a times 1 that follows this, but we can ignore the times 1. So, Ella, how about this one? What's going to happen with log base e of e to the 100 power?
It's just gonna equal 100.
Yep. So we're using this part again. And you're exactly right. It's just going to equal 100. Beautiful. So, nice, nice, nice. All right. How are we looking at that one? All right. We're going to start working these problems in the opposite direction for a little bit. That is, we're going to start out with something that's one logarithmic term, and we're going to expand it into other logarithmic terms. Now, let me talk about the idea of expand. Let's see. Expand. Don't copy this down. Expand the log. And give me a second here. Log of. So sometimes people give kind of a literal interpretation for what you mean by expand the log. Now, expand the log really means you're going to use your product rule and quotient rule to start rewriting your logs. But a more literal interpretation of expand the log would be something like this. So here's your logarithm expression, and then this, and then this. All right, a couple smiles. It's a tough crowd here, man. Wow. All right. Well, let's go back to example E here. Example E. Sydney, as somebody who appreciates grammar, I thought you would have liked that one.
Thank you.
Log base 7 of 5x squared over y cubed. The idea here is to use your properties of logs, and we need to expand log. So your directions are going to say something like that. That means use these properties until they no longer apply. Now you've got three choices to start out with: the product rule, the quotient rule, and the power rule. And all of these are present here, but you can't use the power rule just yet because this 2 only applies to the x, and that 3 only applies to the y. You can't use the product rule because I don't have something times something else by itself. So you have to start out with the quotient rule. And the quotient rule says you're going to rewrite this as the log of the numerator, which is 5x squared, minus the log of the denominator. Okay. Nice. So we used my quotient rule. Now what other rules can I use? And you got a 2/3 chance of getting it right. What rule can I use in this first logarithmic term? Let's look back. I don't have a quotient, so it's got to be one of these two. And I do have something which is a product, log of m times log of n. So I have a product. This becomes log base 7 of 5 plus log base 7 of x squared. There's still something else I can do here. I'm still not quite done with all my properties. Hattie?
The exponents put them in front of the log.
Yes, exactly. So these exponents come out in front of the logs. So that's log base 7 of 5 plus 2 log base 7 of x minus 3 log base 7 of y. Beautiful. And that's it. You're done. You want to keep using these properties until they no longer apply. Let's try another one like that, actually 2 more like that. Let's see. I'll still regard this as part of example E here. Let me start with this one. ln of the square root of x to the 9th plus 6. Well, let me remind you that I can write the square root of something in a different way. The square root of something is something to a power. What power?
1/2.
1/2. Thank you, ladies. 1/2. And now what can I do? Well, now the 1/2 comes out in front. So I get 1/2 ln of x to the 9th plus 6. Okay. Now if you look at your sheet, do you see this rule anywhere? Or look at the handout, it's on D2L. Is there anything about the log of a sum equaling the sum of the logs? Can I distribute the log?
Yeah.
It's tempting, but the answer is no. If there was a property like that, I would give it to you. But there's not. And this is a polite way of saying, we're done. That's as far as you can go. So you might want to go farther, but that's it. It's as far as you can go. Yay. All right. So, hey.
That was easy.
Yes, thank you. All right.
Never gets old, does it?
I you know, the commercial's long gone, but I still like the button. Okay, so let's try another one. And I kind of did this as a warm-up so that we could use it later on when we need it. Log of y to the 9th over the square root of 5x. Where do you want to start? What do you think we should do first?
Get rid of the square root.
All right, get rid of the square root, quotient rule. Both are good answers. So let's see. I heard get rid of the square root first, so let me do that. That's log of y to the 9th divided by 5x to what power? Y to the 9th over 5x to the 1/2 power. Nice. My morning class said get rid of this, the quotient by using the quotient rule. Both of them are fine ways to start out. If I were to use the quotient rule, that'd be the log of the numerator, log of y to the 9th, minus log of the denominator, log of 5x to the 1/2. Okay. Now what? Ideas?
Put the exponents in front.
Yeah, let's use the power rule here. So it's going to be 9 log of y minus 1/2 log of 5x. And let me write the next line here and see if you can spot the mistake, because it's so easy to make. Right here, I'm going to use the product rule. So that's log of 5 plus log of x.
Not distributing the exponent.
Supposed to be the 1 before the x.
Yeah, a couple of you getting that, that's really good. So let me put this inside of parentheses like this. And that means when I expand this, the parentheses are still here. And that means I need to write this as negative 1/2 times there, or if I wanted to write it without parentheses, it'd be 9 times log of y minus 1/2 log of 5 minus 1/2 log of x. Now, on WebAssign, they'll simply mark it wrong. On an exam, if you do a mistake like that, you'll lose a point. You're not going to lose all credit. So, but it is important to distribute this properly, or leave it with parentheses out in front. Either way is fine. I don't really particularly have a preference, just as long as you get it right. Whew. All right. All right. Comments or thoughts on this one? Doing all right? Well,
Actually, I do have one comment. So basically, you treat the coefficient and x as different terms as opposed to what you usually do. Just like,
say that again?
almost like you treat the coefficient and the x, like the x as two different terms, basically, just as opposed to one.
Yeah, these are two different terms.
Yeah, so.
Yep.
Yeah.
Yep. Okay. Let's see. Log base 9 of x times x squared plus 3 divided by the square root of x squared plus 3. Minus 3, my bad. Should be a minus 3 in denominator. Not that overall it's going to make a big difference to our work in the problem, but let me just keep it consistent. What rule am I going to start out with? I got 3 basic rules: product, quotient, or power. Which of those basic rules should I start out with? Quotient rule. Good. So before I do it, write down what the quotient rule is going to make this look like when we use the quotient rule to expand this. So quotient rules is going to be log of the numerator times log of the denominator. Log of 9 times x squared plus 3 minus log base 9 of the square root of x squared minus 3. So it's just log of the numerator minus log of the denominator, and I need another parenthesis there. Thank you. It's tempting to distribute this. That's not the way I want to go on this one. Because if you distribute this, it's a dead end. If you distribute this, if I add log base 9 of x cubed plus 3x, that's as far as I can go with it. Because there's no properties of logs that apply to sums. So that would be it. So let's not do that. Instead, right here, what could I do? Don't make Sydney do all the work. What property applies here? Power rule, quotient rule, or product rule? You've got three choices. Which one?
Product.
Product rule, good. So you've got the log of, in some sense, m times n, this times this. So it's going to be the log of x plus log of x squared plus 3 minus log base 9 of x squared minus 3. I might start wanting to write that as a different way, or in a different way. Jason, what could I write that as? Square root of x squared minus 3. What's a different way I could write that?
To the power of 1/2.
Perfect. X squared minus 3 to the power of 1/2. Nice. Noah, that allows me to do what other rule here?
That would be your inverse property. Nope.
So what would I write then next? What's my next thing I'm going to write here? Well, it's one of our three properties that we're going to use here. Sean, some help?
You can bring the 1/2 down, put it behind the log or at the start of it.
Yep. So we're going to use the exponent rule, or the power rule here, I should say. That 1/2 comes out in front. So it's your power rule. The exponents become coefficients, and that's the great thing about logs, is this property right here, is that it brings that out in front. That's what's going to get all our work done. Can I go any further? Are there any more products? Are there any more powers or quotients? Well, there's certainly no more quotients. You can look and say there's some powers, but those are inside of a binomial. And I can't break this up anymore, so yeah. That's it, you're done here. All right.
It's actually pretty fun.
Those are good problems. Those are good problems. I like going the other direction with these problems too, taking stuff like this and turning it into one logarithmic expression. We'll work on that after we do one more example here, and it's this one. And I want to be, let's see, it's going to be log of the square root of x to the 5th times the square root of y times the square root of z to the 5th. So, wow, kind of a crazy expression there. Square root of x to the 5th times the square root of y times the square root of z to the 5th. There's a lot of stuff that's nested here.
They're all under the first square root.
They're all under the first square root. So let's try and parse all that stuff out. Okay? I'm going to start in the middle here with z to the 5th. Now z to the 5th is surrounded by a square root. So a square root is really something to what power? Something to the 1/2 power. All right. Now that, both of those are underneath another square root, which is y. And that's underneath something to the 1/2 power again. And I'm using the color in here to try and show you how these are nested. And that's important here. Now I've got one other term here, it's x to the 5th. But that again is underneath a square root. So let's take care of that. So that is here, and that's all to the 1/2 power as well. All right, there's a lot of exponents here, and we're gonna slowly unpack all this stuff. So let's see how that looks. Let's get rid of the parentheses here. What is the 1/2 going to do to the log term there? Or is not the log term, but the exponent term there? These exponents, do they add, subtract, multiply, or divide?
Multiply.
They multiply. So this would be y times z to what power?
2.5.
Okay.
5 over 2, right? You think of that as being 5 over 1 times 1 over 2. That's going to give you 5 over 2. So I got rid of that middle parenthesis. I still have a lot of stuff going. It's not written here, but what's the exponent of y understood to be? 1/2. Or no, pardon me, 1.
Oh, shit. Sorry.
Now, this exponent here is going to multiply each exponent on the inside just like it did with the previous one. So this is going to be log I'll have an x to the 5th. What are the other two exponents in here? Jacqueline, can you help me out maybe? Y to the 1/2, because 1/2 times a 1. What's 1/2 times 5 halves? 5 over 4. Nice. So these exponents, every time you're removing those parentheses, these exponents multiply. We've got to do that one last time. And that one last time, this 1/2 is going to multiply each of these exponents in here. See if you can't race me. What's it going to be? X to what power? Y to 1 power? Z to 1 power? Don't shut out the answer just yet. Multiply each of those exponents by 1/2. Nice, 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 nice. Let's see. Robert, what's that going to be up here? 5 to the, or 5 over 2, y to the,
over 4,
and z to the,
5 over 8.
nice, perfect. This is really nice. This is like what we had earlier. This is the log of a product becomes the sum of the logs. So this would become the log of x to the 5/2 plus the log of y to the 1/4 plus the log of z to the 5/8. Almost done. Almost done. Reagan, what's the last property I'm going to use here?
Power.
Yeah, the power rule. These exponents all come out in front. So it's 5/2, the log of x, plus 1/4, the log of y, plus 5/8, the log of z. That, finally, is it for this problem. Wow. I don't think I'll hit the that was easy button on this one, because that was not, I need a that was an easy button. That'd be kind of cool to have. All right.
We don't have anything like this on the exam, will we?
I actually was thinking to myself that I kind of like this problem. Yeah,
No.
to be honest.
No.
But, you know, if I give you these heads up ahead of time, then, you know, at least you can't say you're surprised. That's a good problem. It makes you deal with your properties of logs and your properties of exponents, going between square roots and exponents. From an instructor's point of view, it brings together a lot. And so it's a good problem in that sense. It might not be very fun. I don't pretend that. Don't pretend that at all. But let's do some that are a little more user-friendly. And now we're going to go back to combining into one term. So example F, if you're kind of following along from the handouts that I didn't print out for you today. 3 ln of 2 plus 4 ln of x minus 1/2 ln of x plus 3. So the instructions on this are going to be to write with one logarithmic term. So how do you do that? Well, we're going to use our properties of logarithms and kind of what I keep on calling the backwards direction. I think it's because I think of this way is the forward direction. Here we got to use it backwards. Now, in order to use it backwards, to combine things, the coefficients need to be 1 or -1. And I actually like it best when we're dealing with coefficients of 1. I think it works out nice and easy that way. So what I'm going to do is I'm going to bring these coefficients up into the exponents. This is ln of 2 to the 3rd power plus ln of x to the 4th power plus. Now if I'm writing a plus here, that means I'm taking what and putting it in the exponent. -1/2. And the beauty of this is that now that all these things are written with a coefficient of 1, you can just write it as the log of the product. ln of, actually that's a 2 to the 3rd. Better yet, what's 2 cubed? 8. So I'm going to write this as 8 times x to the 4th times x plus 3 to the -1/2. If all WebAssign is asking for is for you to write it with one logarithmic term, you're done. But on the exam, I'm going to ask for a little bit more. I'm going to want you to write it with positive exponents. So for me, you're going to need to rewrite this as ln. This stuff stays in the numerator. It's only the thing with negative exponents that's going to go down into the denominator. X plus 3 to the 1/2. Notice that in putting in the denominator, I got rid of the negative from that fraction. And that is it. That last one is what I'll be asking for on an exam.
We square, we put.
You could write the square root. I mean, I kind of like that if you take the time to write that as a square root. It's not necessary in order to get the problem correct. I will accept either of those two answers. WebAssign might even accept this one. I guess it depends if they put in a little clause about having a positive exponent or not. If they do, then you're going to have to do one of these two. Let's back up to this part right here. This is in my mind where all the magic happens. When you have the sum of logs and can just squish it down into the log of a product, that's gold. So let's see if we can't practice that again. And I'll give you a quick one to practice that one with. So let me just give you another one here. And you know, again, you're gonna write it with one logarithmic term, right? Using one log term. So it would be this. Ready, go. I want to see some faces. I want to see who gets this one first. All right. All right, winner, winner, chicken dinner. Good job, fella. All right. No one else. No one else is getting. All right, there's another sort of half smile. Angel's got an ah ha ha. All right, what is it? Log cabin, yeah. Too funny. All right. Give me a little love on that one, all right? It's not too often I can build in a joke into my lectures like that. All right. Let me just double check here with, I think there's one last one that I want to do. All right. It's this one, and it's going back and making you think about your graphs of logarithms. Now, both of these are examples of multiple graphs, and they're trying to get you to figure out, well, what set of graphs is the graph for log base 2, log base e, log base 5, log base 10. None of them are the correct answer. Why? Why couldn't either pair of graphs be the correct answer? What are they missing? Now, if you think back a little while ago, when we were talking about these types of graphs, the logarithmic graphs, there was 3 things that I said they all had. One of them we can see here. They all have x equals 0 as a vertical asymptote. Okay, so they got that going. They all grow really, really slowly. I mean, in particular, log base 10 of something is going to grow very slowly. You're going to have to go out onto Main Street, to our east, in order to graph this when the graph gets up to 3. It's really slow growing function. So what are these features? What features missing from these graphs that they should have? Well, let me see if I still got it here. I think I do. Here's all different graphs, and let me kind of look at them one at a time. Here's a graph of log base 2 of x. Here's a graph of log base e of x, and then log base 5 of x, log base 10 of x. But all of them are passing through this one point. All of these graphs have to pass through 1, 0. And none of them do on our previous set of graphs. Actually, maybe one might, but they don't. Other than that, these things got all the things you need. In particular, I want to draw your attention to the fact that this graph never touches the x or the y-axis. That is, you can only take the logarithm of something that's greater than 0, not even equal to 0. If you try taking the log of 0, your calculator is going to bark at you. It's probably going to say something like domain error, log of 0. It's not going to like it. Yeah, domain error. So, okay. Comments or thoughts on all the stuff that we've covered here? All right. Let's call it a wrap on section 4.4. Good luck.